We're going to talk about section 12.5 in our book, Vectors in 3 Dimensions. So we're going to get coordinate axes in 3 dimensions that isn't really intuitive. So this is supposed to look like a corner, if you can imagine, and the x comes out from my iPad or from the board. The z goes vertical and the y goes horizontal. That's not the way most people would think of it. We also have what's known as coordinate planes. So we have what's known as the XY coordinate plane. And so that is, if you look at the X and Y axis, then that plane, I'm going to try to make it look like a parallelogram. So this thing down here that hopefully looks like it's parallel to the floor. There's also the YZ coordinate plane. And so that is the plane formed using the Y and Z axes. So that's going to be kind of this one parallel to the back wall, if you can imagine that. And then there's also the XZ plane. And the XZ plane is, as you would expect then, I'm going to try to make it look like a parallelogram and try to make it look dimensional. And it's going to be this thing that's parallel to the side wall. So those are the coordinate planes. Any point is given in alphabetical order, so x coordinate, y coordinate, z coordinate. Just as in 2 dimensions, we have quadrants that go 1, 2, 3, 4. We have what are known as octants in 3 dimensions. So going back to our x, y, z axis, the z coming up vertical is the positive, and going down, if you extend that down, that's where the negative z's lie. The positive x comes out from the board, and the negative x goes back into it. The positive y goes right, and the negative y goes left. So if you can visualize that, we get what's known as, we call octants rather than trying to number them 1, 2, 3, 4. Sometimes we call the first octant where the coordinates go positive, positive, positive. But in general, we just name the octants by the sign of their coordinates in that octant. So we might talk about, for example, the negative, negative, positive octant. And hopefully that makes sense. The negative x means it's going backwards, the negative y is left, and the positive is up. So it's that back, left, upper octant. Now, even something seemingly as simple as plotting a point all of a sudden gets way more complicated when we are in 3 dimensions than it is in 2. So I'm going to redraw an axis here, and we'll talk about there's kind of 2 different ways that you can represent a point in 3 dimensions. And I'm going to assume here, just because it's easier to visualize, that the A, B, and C are positive. So we would come out A on the X, and we would go right B, and I'm trying to make my tick marks kind of parallel to the other coordinate plane there. So there's B, and then C, I would come up here. Now, one way to do this is to try to draw a box and then show the point as a corner, a vertex in that box. So I'm going to try to here use my not great artistic skills here to try and represent the point is going to be out here. If you can imagine that, that is our point ABC. Now, the other way is to just kind of go a path out there. So I'm going to, in red, we could start at the origin. We could go out A and then over B, and then up C, and then put an arrow on there. And so kind of tracing that path is a second way to represent that point ABC. So nothing comes easy in 3 dimensions. So let's talk about also, so we have this, I'm going to call the point down here at the origin, I'm just going to call O. And so we can see that there is a vector. See, what color do I want to do? I'll go, so we have vector OP that goes from O to P. So if you can imagine this, kind of visualize this coming out this way here, then the magnitude or length of OP also is a bit challenging. So we're going to first look at finding this distance down here. So you can see that this length right here, which I'm just going to call maybe C for right now, let me call it L for right now. So that is the diagonal of that right triangle down on the plane, the XY plane parallel to the floor there. So we're going to have that, I can call that, well, I'm going to say L is equal to the square root of, and that's going to be A squared plus B squared. So that's going to be that green diagonal length there. And then if I use that length L, and I use this as, call that, well, that's length B from here, then this diagonal that we're trying to find there, I'm going to call that, well, that is our vector OP, then we can see that's going to be the square root of the L squared, which is going to be our square root of A squared plus B squared squared, plus that this length actually is C, the same as that length right there. And so it simplifies very nicely into the square root of A squared plus B squared plus C squared. So very reminiscent of what we would do in 2 dimensions. In a similar fashion, we can say that the midpoint, let me get my pen to cooperate here. So we can say the midpoint, so the midpoint M of that vector OP is going to be, well, let me say, not necessarily OP, but the vector, the midpoint in general of, say, vector A, I'm going to make up one here, come on pen, vector AB, where A is going to be the vector, we'll say x1, y1, and z1, and B is the vector or point, either way, x2, y2, z2. Maybe this is going to be easier to think of as points. So let's think of A and B as being points. And then what we can see is the midpoint of AB, I'm going to call M, is going to be the average of those coordinates. So we will add the x coordinates and divide by 2, add the y coordinates and divide by 2, and add the z coordinates and divide by 2. Very similar to what we would have done in 2 dimensions, where we'd have been just averaging the x and the y coordinates. We can squeeze in here the equation of a sphere will look very much like, in 3 dimensions, will look very much like the equation of a circle in 2 dimensions if we say the center of that sphere is the point x sub 0, come on pen, x sub 0, y sub 0, z sub 0, and the radius of our sphere is r, then our equation is going to be x minus x sub 0 squared plus y minus y sub 0 squared. My pen's not doing great. And then plus z minus z sub 0 squared is equal to r squared. So that's very reminiscent of a circle, if you recall, which in 2 dimensions is x minus h squared plus y minus k squared equals r squared, where the h and the k are the center. So just upping that 1 dimension there. So I'm going to go to a new panel here, and we can say then a line. So a line containing, we'll say the point x sub 0, y sub 0, z sub 0, and with direction vector. If you remember how we did this in 2 dimensions, the direction vector is going to be A, B, C, which we can write with these angle brackets, or they can just be with parentheses, is given by, and again, you can do either with regular parentheses or with the angle brackets indicating vector. X, Y, Z will be the starting point. X sub 0, x sub 0, y sub 0, z sub 0, plus anything, any number t, the parameter t, times the direction vector ABC. And from there we can, so this would be considered a vector equation that we just have written up here. And from there we can get parametric equations for that line. So parametric equations are just going to come exactly from this relationship right here. Okay, it will just be x, come on now. So we will just get x, or x of t, is equal to x sub 0 plus a times t, and the y will equal y sub 0 plus b times t, and the z will equal z sub 0 plus c times t. So those are the parametric equations for that line. Dot product, just what you would expect in going from 2 dimensions to 3 dimensions. It's going to be just x1 times x2 plus y1 times y2 plus z1 times z2. So just what you would like it to be. We can also talk about the angle theta between those 2 vectors. So the angle formed, come on pen, it's not showing up here for me. So between, let me try this in a different, I can't even erase it. Well, this the angle between, I'm going to pause it here and see if I can fix this. Well, let's see if this helps. Nope, so I can't find a place where this will even write. We'll try it with the yellow here. So the angle between U and V is, as we've seen before, it's going to be the cosine of theta is equal to U dot V over magnitude U, magnitude V. And so to find then the theta, we'll do the inverse, cosine. So let's see if we can try an example here, if I can get it written down. So if A is the point 0, negative 2, negative 1, 0, negative 2, negative 1, and B is the point 3, 4, 1, and C is the point 5, 0, negative 3. Then can we, A, can we find the midpoint of vector AB? So midpoint, this pen is really frustrating me. Midpoint of vector AB. And in B, can we find the cosine of angle B? And then can we find the sine? It's supposed to be sine of angle B. And then can we find, we'll use that sine of angle B to find the area of triangle ABC. I don't know why this is so difficult to do. Okay, so there's supposed to be a C there. All right, let's see what we can get to go here. So we find the midpoint of vector AB. So I'm going to come here. I'm going to try to come up here and say A is going to be, we're going to go 0. So our midpoint is going to be 0 plus 3. We're adding the x-coordinates and dividing by 2. And then we'll get negative 2 plus 4 and divide that by 2. And then we'll do negative 1 plus 1 and divide that by 2. So our midpoint is going to be 3/2. And negative 2 plus 4 is 2, divided by 2 is 1. And then we're going to get 0. So there's our midpoint, if you can read that. 3/2, 1, 0. Now the cosine of angle B, to find that, the cosine of angle B is going to be, we want to take, so we want to find vectors that have B as its vertex. So what we need is to find vector BC, and we need to find vector BA. So we want to have both those vectors starting at B so that they will have that vertex B that we're looking for. So from B to A means we're going to take the 0 minus the 3. So that's going to be a negative 3 for vector, that's BA. Okay, so that's going to be, let me bring that back up. That'll be a negative 3 for vector BA. And then we'll take the negative 2 minus the 4 will be a negative 6 for the x-coordinate there of our vector BA. And then negative 1 minus 1 will be a negative 2. So there is our vector BA. BC will take the 5 minus 3 is going to be 2 for the x component. And we'll go 0 minus 4 is negative 4. And then we'll go, I think that's a negative 3 minus 1 is a negative 4. So there are our vectors. And we're going to dot those. So we want to take BC dotted with BA. And then we're going to divide that by the magnitude of BC. If I can get it to right. Times the magnitude of BA. Okay, if I can fight my way through this. So BC dotted with BA is going to be 2 times negative 3 is negative 6, plus negative 4 times negative 6 is positive 24, and negative 4 times negative 2 is a positive 8. And in the denominator, we're going to get the square root of, let's see, the magnitude of BC is 2 squared, which is 4, plus 4 squared, which is 16, plus negative 4 squared is another 16, and then we're going to multiply that by the magnitude of BA, so that's going to be 9 plus the negative 6 squared is 36, plus the negative 2 squared is 4. So let's see, on top we've got 32 minus 6 is 26. And in the denominator, we're going to have 20, 36. Square root of 36 is 6. That was nice. And then we have 49. Square root of that is 7. Oh, this was carefully constructed. So I guess we could reduce the 26 with the 6. So that's going to be 13 in the numerator. And in the denominator, that's going to be 21. And we want theta will be the inverse cosine of that 13 over 21. If I can write it. Okay. And I believe that's going to be 51.8 degrees. You can check me on that. Hold still screen. It's going to be, this is the problem of being left-handed. My hand is on the screen. So that's going to be our theta. Whew. Okay. Real quick. So we had that I think the BC was 6 and the BA was the 7. So we know, if I can bring my pen back up. So we've got B is 51.8 degrees. And so we can find the sine of B. And I believe that is going to be about 0.7854. Now we can use this to find the area of our triangle. So kind of an interesting relationship. So if this is our triangle, and we have, say, A is here, and B is here, and C is here, and we'll name the side lengths little a, little c, and little b, and we can drop in that perpendicular h, then we know that the area of a triangle is 1/2, and for us, base times height would be a times h. Now, by the same token, looking at that right triangle that we have created in here, then we can solve that for h. We know that the sine of angle B is the opposite h over c, and so that means h is going to be c sine B. So our 1/2, our formula for the area, 1/2 base times height, which in our case is 1/2 a times h, the h is going to be c sine B. And so this is an alternative formula for the area of a triangle. And in our case, we can see, since we know the angle B, then the other sides are going to be, for us, the BA and the BC, the two sides that make up that angle. So our area is going to be the magnitude of BA times the magnitude of BC times the sine of angle B. And we know all of those from earlier. So I believe side length BA, was that the one that was 7 or 6? I'm going to go back and take. So it's going to be 6 times 7, and we said the sine of B is at 0.7854, 0.7854, and if we throw that in there, I think that's going to be about, let me make those quickly, about 16.5. Okay, and then let's also find the value of k. So we're going to find the value of k. Now my pen seems to be working just fine. I don't know why, but I'm grateful. If we have 0, k, -3 is perpendicular to AC. So for two vectors to be perpendicular, remember that means their dot product is going to be 0. And we're going to use that. So our vector AC, if we go back, I don't know if we actually figured that one out, but AC is going to be, let's see, 5 minus 0 is going to be 5, and the 0 minus -2 will be 2, and the -3 minus -1 will be -2. So there's our vector AC. So if we dot these two vectors together, we're going to get 0 times 5 plus 2 times k, and then plus -2 times -3, and we want that to be 0. And if we do that, we're going to get 2k, and if we subtract that 6 to the other side, that's going to tell us that k is -3. All right, hopefully that's enough to get you through homework number 12.